Okay, so take your seats. Let's start. It's like 11 a.m. right? So I would like to thank you everyone for coming. This is my first time teaching this course. I will teach about the chapter 4, data warehousing, and I would like to thank the others who did not come here. I really feel less pressure. So thank them also. So I would like to introduce myself first. My name is Men Jiang. I'm a postdoc in UIUC since last year, last August. My office is 2130. So if you want to come by to talk, no problem. I'm there like from 8:30 a.m. to 5 p.m. And I got my PhD last year from Tsinghua University, which is a top school in Beijing. My research topic is data-driven behavior analytics with networks. Talk about the behavior analysis. It's like think that you are the governor of the world. That the residents are plants and zombies. So now you want to know who are the plants, who are the zombies, since you just know they are residents. If you do approach driven by experience, you will say the residents who look strange could be zombies. So the residents looks beautiful could be plants, right? So, but the problem is that's a bitter melon, right? He looks really strange, so maybe you will say he is zombie. So then the experience-driven approach will make mistake. But how about we use the same methodology from the observation to representation and go to the models or algorithms? But now we do data-driven, which means that we observe from data, we represent with data, and we model the data. Maybe we can have accurate prediction and detection. So all these approaches will benefit from the applications such as the recommender systems and the fraud detection system. Example is, so how to predict what the user wants to retweet on a Twitter. The experience-driven approach will say you can try popularity, you can try personal preference, you can try interpersonal influence, which means that the close friend will give you some tweets that you really want to retweet. But from the data, can you really observe such kind of factors? Right? Can you model the factors in a scalable algorithm and to boost your surveys in Twitter? So that's a question. And for the fraud detection, it's also the same. So how to detect the fake accounts in Twitter? Well, you know there are many people who want to look famous, so they purchase for lots of fake accounts, fake followers from some companies, which means that you can use just the $200 to get over 100,000 followers. Looks really famous. So how can you detect them? So the experience approach say how to detect the fake accounts. We'll use some features like if the account has too many followees, or if he tweets lots of hashtags, lots of URLs in his tweets, he looks fake, he looks strange. But for the fake followers who really want to, their goal is to inflate the number of the followers of their customers, so they don't have to tweet anything, and they don't have to follow lots of customers. So how can you detect them? Can you observe their strange behavior patterns from data? That's the question. So from my side, I study these three subtopics. So given us the behavior data, the user information interaction, first thing is can you mine the user item behavior network, which means the user and the linking to, it's a bipedal network linking to the products such as T-shirts you bought, such as tweets, papers you wrote. So, but given different time and different location and different brands, you will make different decisions, make different behaviors. So how can you mine the behavior network with spatial temporal context is a problem. Right, the second thing is can you use the unstructured item as content? For example, the tweets is in text. Right? So can you use the tweet content to find some interesting entities, attributes, relationships, to build such kind of knowledge graph and to structure the information network. so that you will know that exactly this user is talking about a president whose name is Barack Obama, and this guy is talking about a football player who is the quarterback, right? So that's how to structuring the information network. And the last one is, since we have done prediction and detection with the behavior network, which has just the users and items, but now we have information network, which is really rich and has lots of type information, right? Maybe entity types like the presidents or quarterbacks, right? So given us this information network to replace the item, can we have more accurate prediction or detection? So that's the integration. So all these three subtopics are my research topics. If you really like them, we can do something, right? If you join the project, I think it's we set the Wisdom Cup Task 2 as our one of the projects, right? So if you know that it's about triple scoring, trying to know extract the attributes from the text to validate that whether this human has such kind of professions or he is from a nation, which nation. So that's the task. I will lead the project with TA Huan Gui, and we will work on this project with other team. Thank you. That's my personal homepage. Okay, so we will go to the data warehousing chapter. Professor Han has introduced the basic concepts of the data warehousing. The most important thing, I think, is the 4 keywords. So, you know, they use keyword. I mean, in the end, use keywords, 4 keywords to define the data warehousing in the last lecture by Professor Han. So, how many of you have still remember the 4 keywords? Put up your hands. I will not ask you to answer. Okay, just put up your hands to let me know you still remember the 4 keywords. No one? Okay, good. One. Okay, definitely fewer than 10, fewer than 5 maybe. So, I agree that maybe this chapter looks, you know, really out of state. I want to let you know how I prepare this lecture. So that I search on YouTube. I search for Jiaowei Han about the data mining, data warehousing lectures. I want to listen to his talk. So there is a lecture there. So that's in Mandarin, I mean in Chinese, which is given by him in 2002. 2002. It's like, you know, World Cup in Korea. So that's really, when I was a high school student, when maybe some of you are still just 8-year-old, Professor Han has already given that lecture. And 80%, over 80 or 85% of the slides are still the same. Okay? So maybe you think this topic is still, it's too old, it's out of date state, but I want to let you know that it's still very important. I want to tell you the importance, okay? So how many of you think that you have already done something about data mining? Data mining, you think your project or something, some homework you did is data mining? Put up your hands. Okay, great. So you have 3 choices to share or work on the data. The first is you can read and share files, maybe via the Dropbox or Google Drive. Okay. The second is you can import the data into database, SQL database or MySQL or something, and you share the database on the server with your friends, with your collaborators. Okay. The third is you can use cloud platforms to share data. Okay. So for the data mining guy, whoever done data mining, so which one did you choose? I mean, option 1, reading files, sharing files via Dropbox with your friends. Put up your hands. Okay, good. Any? So how about the second? You import the data into database and share the database with your friends. Okay, great. We still have some. So how about the cloud platform? Okay, great. Still great. Yeah. So I think some of you really know the importance, but that's too few, I think. So working with, doing the data analysis by yourself is easy. You can just process the files, right? Read the files, write, and do all the data structuring thing, write the algorithms. But that's just for maybe also available for some customers, a few customers when you do some startup, okay? But for a big company that has hundreds of thousands of employers, how can you process the data, especially when you want to report some data analysis to your manager, to the managers who don't code, who never code, okay? They never program. They just can read the Excels, spreadsheets, the tables, figures, but you have the data from operational database frequently updating, right? So how can you report the data analysis to your managers? Right? The managers, they don't care how to program, how to code, but they don't want to make any wrong decision. They cannot make any mistake, right? So I think that when I graduated from the Tsinghua as an undergraduate, I have a roommate, also my classmate. He's a Shanghai citizen. If you know, Shanghai city in China is really big. And after his undergrad, he wants to work in Shanghai. So he joined Baidu Shanghai. And last year, I went back to China to his wedding. He told me he has been a project manager in Baidu team in Shanghai. And he worked for 6 years on data warehousing. And his bookshelf, I can see on his bookshelf, there is a book by Zhao Weihan. And he told me he really listened to some talks by Zhao Weihan on YouTube or on Youku. So it's like we are still classmates. We are still learning about data mining, about data warehousing. Well, it's very important for you to look for, if you want to look for a job in big companies, because it's not just like you do your startup, you read or write your files, or updating your database, and give some feedback. You really want to give interesting analysis to the managers who cannot code, who don't understand code, okay? So data warehousing is very important. Well, let's see. The data warehousing is trying to bridge the data from you can see the operational database on the bottom to the managers, top tier, they as queries, reports, and analysis. So the decision makers will use the front-end tools to understand the reports, to understand the data. But now we can just go from the bottom data from the database to data warehouse, and then we do OLAP. We build an OLAP server to process the data, and with OLAP, we can give reports or analysis to the managers, the decision makers. So for the bottom tier, you can see there are 3 models. The first is from the view of the enterprise. Okay, so for example, let's say the Holiday Inn. They want to collect all the information about the subjects spanning the entire organization, entire hotel. Okay, but the data marts, if you see this figure, this data warehouse can be split into several data marts. Each data mart will be used by one department of the company. You just maybe need part of the data of the warehouse. So the data mart is a subset of the data that will be used by a specific group of the users, which could be just a department of the company. Okay, and another, the last one is virtual warehouse. This is saying that you don't want to use expensive equipment to set up the warehouse, but you have the operational database, and it's really big. So how can you have a view, still like the OLAP or like with the data warehouse? You can set up the view of the virtual warehouse. This is more about the algorithm side. So how to do the data processing in before we build the data warehouse, we have to do these 5 steps. First is data extraction. Data extraction means you get data from the different sources, like maybe operational databases, even many operational databases, like for the customers who log in, who check in, who had breakfast or something about their personal information. And then you do data cleaning. If they give the wrong format of their age, their information, you should do data cleaning. And then do data transformation. If you have lots of database, how can you integrate them together, transform the data into a standard format for this data warehouse, right? And the 4th is do loading. So you should load the data from the database to data warehouse. You should sort, summarize, and if you know that for the OLAP there are many dimensions and measures for the OLAP, so you have to sort and summarize the data. The last one is refresh. Since you know data warehouse is somehow different, it's physically separated from the database. So when the database have already updated frequently, for several days, now you want to update your data warehouse, you should do refresh. Refresh the data warehouse with updates from the sources from the operational database. So here is a set of definition of the data warehouse objects. We call it metadata. So what you should store, manage, and process in the data warehouse. The first is description of the structure of the data warehouse, right? How you organize this data warehouse. The second is operational metadata, like the linking data, relational data, right? And you should have the algorithms used for summarization. Even today, in Jiaowei's group, we have, I think he's also a TA, Feng Bo Tao. He has proposed a very efficient OLAP technique called Event Cube, which is doing the summarization on event data. Okay, so also you should store the mapping from the operational environment to the data warehouse and data related to the system performance. For example, if you use SQL, SQL has administrator, so you can see the CPU cost, you can see the time cost of the processes. So also the same for the data warehouse. You should see the same system performance, right? So in the data warehouse. Also, you should import the business data into the data warehouse. Okay, let's see the data cube and OLAP in data warehouse modeling. How to build a data cube? Data cube has two factors. One is the dimensional table. The other is fact table, or called measure table. So dimensional table means you have different dimensions. Let's say for the sales, so you have the item name, you have a brand, you have a type. So then you can say, okay, I want the supermarket in Champagne, and the product should be Oreo, and the date should be, which date, maybe the last week. And now we want to choose the measure. The other is the measure table. So you want to choose sales. You want to choose the number of the items and the unit price. So different measures can be chosen. Right? So a data cube has these two parts. One is dimension table, one is fact table. Okay, and the data cube is defined as a lattice of cuboids. And there are really, really many cuboids. Next page, you will see the structure of cuboids. And from the top side, you can see this, which means that you can see if we have just 4 dimensions, time, item, location, and supplier, now there are how many? You can see how many cuboids. Right. So first, we have the 0D, which means we call it apex cuboid from all. I mean, we choose all the dimensions. Okay, merge all this together. But now we are just talking about the dimension table, not the measure table. Okay, so we choose all the dimensions, and then we take the 1D cuboid, which means that we take just the time dimension. We take just the item dimension. Or if we just take the time dimension, say 1D cuboid with a time dimension, then we are looking for different time levels, the sales in different time levels. The time there are many time levels like week, day, week, hour, or year, quarter. So for different time levels, you can still see the sales, you can see the unit price. So that's a different measure. Right? So we can see for 1D cuboids, there are 4 cuboids with just 1 dimension. And then if you have 2 dimensions, there will be 6. And 3 dimensions will be 4 again, because you just remove 1 from 4, right? And the last one says that you take the 4 dimensions. But for this, they are different. Okay, for this one means that you merge all the information. You say, well, I just want to know all the sum of the sales, the sum of the sales in the data warehouse. Okay, I don't care about any dimension. Okay? So there are many cuboids. It is a 4D cuboid. To organize data warehouse, you can use 3 schemas. One is called star schema. The second is snowflake schema. The last one is it's called fact constellation, but it's like galactic schema. You can see it's a collection of stars, which means that the star could be, I will introduce later, a star could be a rich table. And so for star means that the rich table is in the center, and you have different key tables outside it. And for the a collection of stars means that you have multiple rich tables as stars. So let's see. This is an example for the star schema. The center is, I call it a factor table or a rich table, which has, you can see these 4 colors. I mean, time key, item key, branch key, and location key. They are dimension keys. Okay, and with different dimension key, it will link to other tables like the item table, location table, item table, and branch table. Different table will show the levels of these dimensions. You can see for time there are. It gives us definitely it should have the time key there. But now you can see 4 levels: day of the week, month, quarter, and year. For the location, there are 4 levels: street, city, and state and country. Okay. So these 3 pink-colored rows are measures. Okay, measures. Say the dollars sold, the units sold, and average sale. So here is the stock schema, which means that we have the key of the dimensions, and each key will link to another table. For the snowflake schema, when we have this kind of example, say when the location share the same city. For example, we want to store different locations like the 4th Street in Champaign. We want to have the 6th Street in Champaign, Green Street in Champaign. So do we really have to take this table? I mean, we will duplicate the information of the city for this street, right? So I mean, all these three streets are in Champaign, so we don't have to duplicate it. Then we say maybe we can say, okay, this street, 4th Street, 6th Street, Green Street, they should share the same key of the Champaign city, okay? And then we have another table give us the information of the city, Champaign, and it has the keys and the values as city. So that's the idea of the snowflake. So there's a trade-off. So which one do you think is better? I mean, the snowflake or the star? Right. Some people say snowflake is better because it can save more storage. Right? You just use a city key, the key of the city, in this location table to represent the city of the 4th, 6th, and the Green Street. Right? But some companies still use star schema because it will save more computing cost. Because when you want to know the cities in Champaign, or you want to know some other information, you have to use the city key, the key of city, to search. You should join the city table and this location table so that you will have these 3 street names. Right? So the computation is, the cost of computation is higher. Right? So some companies still use star schema. And the last one is the fact constellation. So you can see when we have other factor table. So here is one factor table we had, and another factor table is shipping factor table. It still has the 3 keys: time key, item key, and shipper key. And the shipper key will have its own table. I mean key table. I mean dimension table. You can see the shipper name, location key, and shipper type as its levels in this dimension. So now we have 2 tables. They can represent it as, we call them stars. Okay, 2 stars. So when we use the item key table or location key table to link these 2 tables, 2 factor tables, we will call it a constellation. It's like a collection of stars. Okay. Usually, it's in some company, their database or data warehouse really looks like this, very complicated. Okay, so now there are many terms, right? Here we have got from the big, let's go from the big to the smaller. We have the data warehouse. So we have the data cube. Smaller, we have data cuboid. And then we have dimension of the cuboid. So we have different dimensions, and we have maybe the cuboid choose 5 or 3 dimensions, right? We have factors. We have facts. We have measures. And in each dimension, we have concepts. See here, so for the dimension location, we have different levels, like the region, country, city, and office. And for different levels, there are different concepts. For a level like region, the concepts are Europe, North America. And for country concepts, there are level. There are concepts of Germany, Spain, and Canada. So usually, definitely we can use value here, say the value of this level. Okay, the dimension is location, the level is country, and the value is Germany. The level is Spain, or the value is Spain, or the value is Germany. But it's sometimes ambiguous, so we usually use concepts to define this. So another interesting topic is here we give the location dimension. I mean the concept hierarchy of the location dimension. So how can we automatically construct this concept hierarchy from the text, from unstructured data is also another interesting research problem, which is doing in Jarvis group. They're giving us all the news data, giving us the tweets data. Definitely there are entity names like Europe, like Germany, like Spain, and maybe there are some sentences that says countries such as Germany, Spain, and the United States. So can we use this unstructured text to build this concept hierarchy automatically from the text? Right? So that's a very interesting such problem. It's more like in NLP. Okay, so now let's come to the measures. Okay, there are many different kinds of measures. Definitely, they categorize the measures into 3 categories. Let's see one by one. The first is distributive measures. Distributive means you can, when you try to operate the data to have the measure, the value of this measure, the result of the measure, you can distribute the task to different machines. Okay, and if the measure operation allows you to split the cube into different machines to process, to calculate, and then you aggregate the results from different machines, and now the results still be available. You can still compute the final results. There's no mistake, no error, which means that this measure is distributive. Let's see here the counts, the sum, the minimum, and the maximum. So if you have the data, now you say, okay, I want to know the sum. Okay, you can split the data cube into several pieces and distribute them into different machines in the data clusters. And then every machine will compute the sum. Okay? And then you aggregate the results from different machines, and you do sum the results again into a final sum result. And the result is still the same as you do in one machine, which means that this measure is distributive. Okay? The second is algebraic, which means that you cannot just distribute the measure by just one value. So now you are communicating with other machines, other clusters with just one value, say sum function or minimum function, right? But now for the this second category, you have to give more than one value. For example, if you want to calculate the average measure, I mean the measure of average value of the sales. Now, if you split this task into several pieces and distribute it into different machines, and every machine gives you the average value of their data piece, and you aggregate them together, and you say, okay, I will do average function again. Definitely, it's wrong, right? Wrong, because you don't know how many units or how many numbers you give to different machines. Right? So you have to get two values, two functions. One is sum, one is count. So if you get sum value and count value from all the machines, now you do sum function again, and you do count function again, and you say, okay, now I will calculate the average, and you do this dividing function. You divide the sum by the count. Then you have the average. Then it is correct. Right? So it's called algebraic operation. The last one is holistic, which means that you have many functions. I mean, for average, we have two functions, right? We set sum function and count function. But for some other measures, even though you have many functions, it's still not doable to distribute all these tasks into different machines. Okay? For example, here, if you want the median of the data, okay, and you send 1 value or 2 value or 8 value to the machines, still not doable. But you have to get all the data and sort them, and you find the median and you report the result, and it is correct. So that's the case that we want. We want the exact value. I mean, we don't want the approximate value. But definitely, if you change this tasking to, okay, maybe I just want a approximated number of the median. Now, somehow there are some other algorithms that allow you to do the distributive operation or algebraic operations to the hash machines, and you have the approximate median value. Right? So that's still doable, but that's not the exact number, exact result. So here is a view of the Microsoft. I think it's Microsoft DB miner, and it's a program, and you can see the schema hierarchy from the Europe to the countries. Okay, so that's I think that's really old. I think they got this slide in before 2002. I think this software should be super old. Should be run on maybe Windows 97, Windows 3.1. So now let's come to the multidimensional data. So we know that there are different levels for different dimensions. You can see this region. This is location dimension. The level could be region, country, city, and office. Okay, and this is a time dimension for the year, quarter, month, week, day. But you notice that you can see it may not just be a hierarchy or a tree structure. It could be a network or graph. You can see year to quarter to month, year to week, but now month and week can both have the child level as day. Okay, so this is allowed in the data cube. And this is a figure about the data cube, and there are many cuboids there. So this orange cuboid, this is a cuboid. Say we just choose the date dimension, right? We have the date dimension, and we have the country dimension. Actually, we have the location dimension, but now we choose the level as country. Okay, we have the date dimension, the time dimension, but now we choose the quarter as a level. Okay, and for the product, we didn't select this dimension. Okay, so now this orange cuboid is 2D cuboid in the data. So we have 2 dimensions, and this green is another 2D cuboid. It has the product dimension and the location dimension, and but no date time dimension. Okay? And for this gray cuboid, this is a 1D cuboid. It has just this has just the 1 dimension as location at the level of country. Okay, and the last, this smallest, it says all. So all the levels of the products, all the levels of the time dimension and the location dimension. So it didn't distinguish any levels in any dimension. So this is just 0D cuboid. Okay. Now you can see the structure of the. I mean, these two are corresponding with each other. So this is from the 0D cuboid, which is this dark blue cuboid here. And this product date, product country, and date country. I think we have seen the orange one is the date country, okay, and the green one is product country. So we have the date country and product country. So we give these 3, actually 4. Right? We have another is the country dimension. We have these 4 cuboids highlighted in this data cube. And now I want to introduce the operations of the OLAP, typical operation. So the first operation is roll up, or people may call it drill up. The second is drill down, and may call it roll down. Actually, the verbs can change each other. So for the roll up means that you can. I think we have another a previous slide which can show this. Okay, this one, this star schema. So if you want to do roll up, I noticed that this figure is somehow not that perfect because it goes from the small unit, the small level, straight to the big level. I mean, from the lower to the higher. But usually we started at from the higher to the lower, maybe from country to state to city to street. Okay. So if you do roll up, means that you are going up. You have fewer values of the level, so you go for the higher level from the street to country. And the drill down means that you are going from the top to the bottom. You are going splitting the country into different states and to different cities to streets. Okay, so that's the roll up and roll down operation. And the third operation is slice and dice. It means that you can project the cube or select the cuboid. So the project means that you can eliminate one of the dimensions. Okay, you go from the product country and you say, now I want to project the dimension of product. So we can go to the country. Okay, so from this cuboid to this cuboid. And the dice means you can select one of the level. So you say, okay, when I operate this cuboid, I want to remove, or I want to just select the first quarter. Okay, so that I can just take this part of the orange cuboid and then do next operation to be drill down or drill up. Okay, so that's slice and dice. And also you can do a rotate pivot for the data cube, which means that you can visualize this from 3D to 2D. Actually, it's similar to projection, to slice. And the last two operations, first is drill across, which means that you can here. So you want to go from the product date to product country. Okay, you don't have to. Actually, it's two-step operations. You can first drill up to. You can first project the dimension of date, right? And then you add one more dimension, country, which means that you dice it. And but now you can just do the drill across, means that you can go from the product date directly to the product country. You say I want to drill the date across to the country. So you go from the product date to the product country. And the last one is drill through, which means that when you realize that in your data warehouse, data cube, you don't have that dimension. You have to go back to the backend relational table or operational database using SQL to extract that bottom level or that dimension of the data and go back to this data cuboid. You add one more dimension. For example, if you want to add another dimension, could be, let's say you have location time, maybe color or something, right? You want to add another dimension, right? And then you realize that in this data cube, there's no dimension called color. So you have to go back to the database and extract all the color information of the products at different dates, at different countries, and to refresh this data cube again, and then you put the color in this cuboid, which is called drill through. It's a really complicated operation. Now, here, this figure is really hard to look, but it shows different operations in this table. The first, let's see the roll up, which means you can see here is the original data cube. So this is the item type dimension. It has entertainment, has computer, security, right? This is the time dimension, has quarter 1, quarter 2. This is the location dimension in city level, has Toronto, New York, Chicago. So the number could be sales as a measure. Okay. Now we want to do roll up, which means that we can say, okay, let's roll up the location from cities to country. Okay, from this city level to country level. So now we have the Canada, USA, instead of Toronto and New York. Okay, this is rolled up on the levels. And we can do drill down, which means that we can drill down the levels of the time dimension. Now this is the level is the quarter. And now we can drill down into months. Okay, so we have the January, February, all these months on this dimension, on the time dimension now. And so this is called drill down. Definitely we can drill down again from the months to date. And this is doable. And this part is dice. So we can say, okay, now for the time dimension, we just want quarter 1 and quarter 2. Okay, we just select these 2 quarters. And for the location, we just want the Canadian cities. So we have Toronto and Vancouver. So we remove the New York and Chicago for this dimension. And now we have a smaller theta cuboid, which is, this is called dice operation, or we call it select operation. Select is really like the SQL. Right? SQL has select query. And this is the slice. Slice is say that we want to project the data cube into by removing one of the dimensions. So here we slice the data cube by removing the time dimension. So we have just the location dimension of Chicago, New York, Toronto, Vancouver, and we have the item type dimension of the computer and security and phones. Okay, and definitely we can do pivot, or we call it rotate operation. So we can put the item type dimension into the vertical line, and we can project, we can rotate the location dimension into the horizontal. Okay, so these are the two, actually 1, 2, 3, 4, 5 operations, standard operations of the OLAP operation. Okay, so here is a query model. So when we want to find an appropriate data cuboid, how can we do this? And how can we use visualization to show which dimensions we chose, and the levels we selected? Okay, so from the original point from the center, every black line from the original is a dimension. So we have this is customer dimension, product dimension, organization dimension, promotion, location, time, and shipping dimension. So we have all these 8 dimensions. And for different dimensions, the orange points are the levels. Okay, you can see for the time, we have daily, quarter, annually. We also have all these dimension levels on this dimension. And also for the product type, product line, product group. Okay, so now we say what cuboid we want. We want for the to analyze. Okay, so we say, okay, we want to choose, we want to select 5 dimensions, and for each dimension, we want to have these levels. For the customer orders, we have the contracts, this as a level, and for the time, we want a quarter. For the location, we want country, and for the district, for the organization, we want a district instead of division or salesperson. So for the products, we want a product group. Now we go on this green line, and comes this kind of circle shape, and we say, okay, this is called, we walk across 5 footprints, and we query the 5 levels of the 5 dimensions from this start line. This is called start line. Then we can say, okay, now with this selection, we can generate a cuboid to analyze the data. So with the data cube we have selected, I mean, maybe here we have 5 dimensions. Definitely in here we just have 3 dimensions. It's easier to visualize 3 dimensions. Visualize a 3-dimensional cube instead of 5. I really don't know how to visualize 5. I can just show 3 at a time individually. So now you can see if we choose a sales measure, the measure as sales, then the size and the brightness and the density of these small cubes are the value of each levels. Right? So the location could be New York, and the product could be phone, and this is the outdoor products. Right? So, okay, the product is outdoor product, and the location is the location is Europe, and the revenue is from 0 to 2,000. So this cube, this is not called a cube. Like anyway, this represents the value of the revenue on these levels, like the Europe and the outdoor products and the 0 to 2,000 revenue. Okay, and the size and the brightness will show this value. This is for the visualization. Okay, now we come to the design and the usage. The design of data warehouse depends on the users. Okay, so we have 4 types of users. So that's why we have 4 different views. For the top-down view, which means that who are operating the data warehouse, they want to select the necessary information from data. Okay, so that's the top-down view. And the data source view, which means that who imports data to the data warehouse. For the users who import the data from different sources, different databases into the data warehouse, they just care about the data source view of this data warehouse. And the third is the data warehouse view, its own view, which means who really manage and first build and manage the data warehouse. They care about the fact tables, which means measure tables, and the dimensional table. Okay, and they design this dimension and measure table. And the last one is business query view, which means that they are the managers, okay, who use the data warehouse for data analysis and decision making. They just want to see the visualization like this or some other much better visualization from the data warehouse. So that's the last view. So for us, the data engineers, maybe we can take care of the data source. We can see how can we import the data from different sources, from PNC Bank on Green Street and the PNC Bank in Havana into the same data warehouse, right? And we should do cleaning, we should do pre-processing, extraction. So that's the data source. And also for data engineers, we should do data warehouse view, because when the managers say, I want the information about the sales on what product from which location, you should give them such kind of operations available, like selection, projection, roll up, roll down. Okay, and for the managers who don't want to code, right, they just share the business query view. They can type some query and they can see the figure, the plots. Okay, so the how to design a data warehouse, you can have these 2 ways. One is top-down, the other is bottom-up. Top-down means you start from the design and planning and build a data warehouse. And why you sit down means that you can split it into different data marts. Right? When your department wants different pieces of data, you split the data warehouse into different multiple data marts and share them with your departments. And the bottom-up means you first do the experiments, prototypes, or even data marts in different departments, and you merge all the data marts together into a data warehouse. Right. So I think, in my mind, I think the top-down is easy, right? But it takes more time, because you have to let all the managers, all the users in different departments to agree your design on the top-level design of this data warehouse. Right? And then you split the data warehouse into pieces, into data marts. They can take the data marts to analyze their data. Right? So that takes time, but it's easier. But for the bottom-up, it's difficult. When you say, okay, I have many managers, or let's say project managers in different departments, and let's say they build their own data cubes. They have their own data marts, and we want to merge. Now we want to merge all the data marts together. Maybe the design are very different, and it's really difficult for you to merge. You have to maybe go from the beginning point. You should process the data again, extract the data. You should clean the data, and then you say, okay, everybody will have the same format. So now we can merge all the data from different marts into a warehouse. But it takes time at the end of the process, but it's very tough. So myself, I think I will choose a top-down, but I don't know others. So from the software engineering point of view, which means that the one is waterfall, so you can do structured and systematic analysis for each group, each step, and the other is spiral, which means that you can rapid generate the functional systems, right? So I think for the startups who really want to build some warehouse, they can choose the second one. But if you want to have, if you have been a senior manager of engineers in Google or in Facebook, and then you jump out, you say, I want to build my own stuff, maybe definitely you have such kind of taste to say, I want to build in waterfall point of view, waterfall style from the senior software engineer point of view. And the typical data warehouse design process, okay, here are 4 steps. Definitely you cannot avoid it because from the elements, I mean as elements of the data cube or the data warehouse, you have to choose all these elements. One is the business process model, the orders, and the second is the level of the data, and the third is the dimension you want to put into the fact table, put into the dimension table, location, time, and the other dimensions. If you want to add more dimensions, when you have already got the data warehouse, it takes lots of time to add one dimension from all the operational database to this data warehouse. And the last one is you should choose the measures. That you say, I want to know the sales, I want to know the unit price, I want to know the number of customers. But you should decide these measures previously, just before you implement the data warehouse. Okay, so when you have already got the data warehouse, you will like it because it can be used for these 3 kinds of applications. One is it can do information processing, so it can support the managers to see the tables, charts, and graphs to know the reports. And the second is analytical processing, so you can for the software engineers who really operate on the data cube, you can easily add more dimensions, remove dimensions. I mean, when you have already got a dimension, but you want to add or remove, I mean, drill down or drill up on the data cube, it's easy to do this. Right? So you can understand, do multiple dimensional analysis on the data warehouse data. And for the data mining guy, think that now you have just the files, right? You read and write, but suppose that you have got a data warehouse. I think it's easier for you to share the data with your collaborators, especially when you have hundreds of collaborators, which is not the case. But definitely when you have hundreds of collaborators, you want to have a built data warehouse to share the data, to operate on the data, especially when the data is like petabytes. So yeah, why not? Now let's see this. So from the online analytical processing to online analytical mining. So why we want to do OLAM from the OLAP? Because when we have just the OLAP, we can report the statistical analysis, the figures, the tables to the managers. But the latent patterns or some interesting discoveries are not shown here, right? So we should do data mining with the data in the data warehouse. And the good thing is the data warehouse provides us high quality of data. Right? The data were integrated and very consistent, and it's clean. We don't have to do cleaning again. Right? So every time we do with a cup computation, I mean wisdom cup or KDD cup, we download the data. Maybe it's not clean. We have to clean it beforehand. So it takes lots of time for the data mining guy. And also, we do OLAM because with the data warehouse, we have the structured data. It's not just like the text, which is not structured. And we can do the exploratory data analysis by drilling down, by dicing, by all the operations. And the last is we can integrate all the mining functions. Say we first do counts, and we do average, we do medium, then we do sum. We can do all the functions together, right, in the OLAP. We don't have to, every time you implement operations or mining function in your program, let's say Python or something, programming language, you have to implement one more function. Right? But here, all these functions were implemented already, and you can take the functions and just integrate them together to get your result. Okay, the last section, so the implementation. A data cube, can be viewed as a lattice of cuboids, and let's say the bottommost cuboid, you know that, right? If we have 4 dimensions, we have the location, product type, we have the time, we have, I remember the last one, but anyway, we have 4 dimensions. The bottommost cuboid is the base cuboid, which selects the 4 dimensions. And the topmost one, say there is just one cell, let you know the sale, or let you know the number of customers, one measure, right? Or several measures, but just one cell on the top of the data cube as one cuboid. So how many cuboids we may have when we have n dimensions, an n-dimensional cube, and each dimension, let's say this I is the ID of the dimension. Okay, we have n dimension, and I is the ID of dimension, and the LI, capital LI, is the number of number of levels in a dimension. For example, dimension could be location and time. Okay, and LI could be, let's say, if location is the first dimension, so L1 is the number of levels in a location dimension. Could be country, region, city, or street. And also for time, it could be L2. Then will be quarters, day, years. So how many how many cuboids we have in the n-dimensional cube with L levels? So this is the formula. But you can see it's not like just a cumulative product by all the Li, but with +1. You know why? Clap your hands if you know the answer. Or you can just speak up. Why we should +1 on this L1, Li? Yeah, correct. So because we have the OR, a level called OR in a dimension. Right? So here we should +1 for the number of levels in a data cube. So you can see this number is really big. When we have 4 dimensions, and suppose that each dimension has 4 levels, right? For location, it has country, city, street, office, so 4 levels. So how many cuboids we have in a cube? Like 625. Right? So 625 cuboids in a cube, 4 dimensions, 4 levels in the dimension. So we don't want to use our disk or our memory to store the 625 cuboids. Right? So there are different ways to implement the data cube. The first is we do the full materialization on the data cube. Say we materialize the 625 cuboids. Right? It's really tough. The second is we do no materialization, which means we don't materialize any cuboid. But when we want to have some data analysis on a certain cuboid, now we do materialization. Right? But it will cost time when you want to do this query, want to build the cuboid. Okay? The last choice is we do partial materialization, which means that you can implement the most frequently used cuboids, but the problem is some cuboid, there's a trade-off between the size and sharing. So size means that maybe you think if I implement the higher level, for example, if I implement the year level, it will take me smaller storage. Right? It's a smaller cuboid because we take the higher level of the time dimension. Okay? But when we want to share this cuboid with others, when they told us that they not want year level, they want quarter level, or they want month level, that's a problem. We don't have that. Right? So we have to materialize the level at the month or at the quarter again from data cube. Right? So this is tough on the sharing. But say if we allow us to have a bigger cuboid to store in our database, in our disk. Say we have a level at month. Now, if the user who want to share our cuboid, say they want year or they want quarter, then we can just do the operation. Right? We do sum, we do drill down, drill up of sum. So then we can give them the cuboid they want. It's easy. Right? So that's the trade-off between the size and the sharing when we do the partial materialization. Okay, so here is something about how to do the operation in the data cube. So let's see. So can we use SQL-like queries or some programming language to define a cube and compute a cube? This is the answer. Okay. So let's see. Here is a guy whose name is Jim Gray, who is very famous. He is American computer scientist. He received the Turing Award in 1998, and he proposed because he got the Turing Award because he contributed a lot on the database and especially for data cube. He proposed this operation called cube by. Right? We have group by in the SQL, but he proposed cube by in this SQL-like language. And this paper was published in RCD 96 and DMKD 97. The citation count is as many as 2,800, I think 2,800. And Jim Gray, his full name is James Nicholas Gray, and he was born in 1944. Here's a link. So he worked for Microsoft for a long time. And he was born in 1984, and he was assumed lost at sea at 63 years old in 2007. So if you go to this, so this is a summary homepage for Jim Gray, and he's very famous in Microsoft. So you can see this line. Say, as you may be aware, Jim Gray has gone missing. So he was missing since 2007 at sea outside California, and in 2012 he was declared as deceased, but we still cannot find his body. That's legend, I think. This is Turing Award winner. So he proposed the cube by, which can be considered as computation with these operations like group by plus cross table plus subtotal. So this is the cube by. So how to? There are two ways to. We have the OLAP, right? So we have the data in the data, like let's say this base table. We have this kind of table in the data warehouse. So when we want to do the SQL-like language to process it, we should build index just like SQL, MySQL for the database, right? So, but you can see for the region like Asia, Europe, type like retail, dealer. So you don't really want to store this string in the database, right? If you can save more space, you can do index, and it's easier for you to search, to query. Right? So, can we how to build a good index? One way is to build a bitmap index. It's called bitmap index. Means that you put for each dimension, you can see you put this region dimension, right? You have the values of the region dimension like Asia, Europe, right? You put all these values on the column as a column name. Then for every record, here is the record. Okay, for every record of 5 records, every record you say, okay, this is the value is Asia. Just match the column name. You put 1 here, and if it doesn't match, you put 0. Okay. For the type, also do the same. So you have multiple index tables. That's called bitmap index. So if the value of each level, let's say for the region level in location dimension, if the number of values, the number of concepts is big, then we will have a really big index table. So this is not good, I think. So the best way to, the most popular way to implement the index is still use B plus tree. Right? better than this bitmap index. And another indexing way to indexing the OLAP data is to do the joint indices. You can see when we have the different tables, different dimension. One is location dimension, one is item dimension for the measure sales. And we say, okay, now we want to, if we frequently want to query for the pairs of location and time, different values, same concept Main Street and the concept Sony TV. So we frequently want to search for this sales results. We should join this two-dimensional table into two column names with the location levels and the item level. And here is how to efficiently processing the queries. So let's see. Definitely, we have different operations we should keep in mind. You can do all this. It's like you remember the select query, the import, the insert, and all these queries for SQL. So you should remember drill down, roll up, and dice, all the operations of data cube. Now you want to determine which cuboid should be selected for OLAP. For example, here this is a quiz like so we want to process for a brand, province, or state with the condition year 2004. And here are 4 materialized cuboids available. So which one should be selected to process the query? So let's go from the first to the fourth. Okay. So who support for the first one? Who support for the second one? Who choose the third one? Who want the fourth, last one? Want both? Great. So good to read the book before you listen to the lecture. Okay. So let's go to the OLAP server architectures. There are 3 kinds of OLAP architectures. One is relational OLAP, one is multidimensional OLAP, one is hybrid OLAP. So for the relational OLAP means that you use a database to store and manage the data warehouse. And for the multidimensional OLAP means you can use multidimensional array to store the data for the OLAP. And the last one is hybrid OLAP, which is frequently used by Microsoft SQL Server. They give the user flexibility to use the data as multidimensional arrays or as relational database. Okay, that's 2 different ways. And for the when I listened to the video by Professor Han in 2002, he just published papers for the relational OLAP. So he had some new papers which was written by Professor Han and his famous student Jian Pei, who is now a professor, also actually fellow in San Francisco in Canada, and some other senior Google scientists of his as his students. They published paper in SIGMOD 2001 and other conferences around 2002. Okay, so that was really popular research area for this RLAP. And since we know that Microsoft SQL Server has very mature implementation on the hybrid OLAP, maybe it's kind of out of date. Okay, let's do the summary. So first of all, Professor Han in last lecture, he introduced the concept of the definition of the data warehouse, and he introduced the 4 keywords. We should go back to see the slides again to remember the 4 keywords. And here I introduce these sections. One is the data cube has dimensional table and measures. The dimension could be location, time, and the measures could be sales, could be number of customers. So we introduce you 3 types of schemas to store for the data cube. One is star, one is snowflake. Remember the trade-off between star and snowflake. Right? If you use P of city to store the information of city, like Champagne. And the last one is a collection of stars called fact constellation. And I introduced you the overlap operations, including drill down, roll up, and slicing, dicing, all these operations. And we introduced the multi-tiered architecture from the bottom data in the operational database to the data warehouse, which can be split into data marts for the departments, and then go up to the OLAP server. And with the OLAP server, you can do the operations and give figures and tables to your managers. They can make decisions. Right? That's a multi-tiered architecture. And we introduced the use, including for the data mining guy, including the information processing, analytical processing, data mining, and OLAM. And the last day, we introduced the implementation on the data cube. So we introduced if we have 4 dimensions, 4 values, 4 levels in each dimension, and we have 625 whole cuboids for the data cube. So how can we materialize the data cube? Right? So we want to do partial, we want to do full, or we want to do no. So that's 3 ways to do the materialization. And we introduced you 2 ways to index OLAP data. So one is bitmap index, one is join index. And then we talk about the query processing and the server ROLAP, MOLAP, and hybrid OLAP. And remember that we also give you some variation on the data cube, right? So the orange, green, and all the data cube. So hope that you also remember the +1, why we should do +1 in the formula. Okay, so that's all. Thank you.你要看那个图，那个图是最清楚的，就是那个特别难看的图，就是那个展开的那个特别难看的图。对这个，对他这个讲的很明白 ，slice 跟 dice。对 ，dice 的意思是说你选了其中的某些 level。slice 的意思是说你去掉了某个 dimension。哦。对，去掉一个 dimension。不一定。4个希望很多，4个只是图不好表示，但是你其实用数学是很好表示，或者程序语言是很好表示的，只是 visualization 的时候会成问题。对。那好，你也是 CS 的吗？是吗？OK， 好，我回头加一下微信，你有微信吗？